Sea level rise. It's something we hear about often, especially in discussions about climate change. But why is it happening, and how do we even measure it? Well, in this presentation, we're going to look at the three key contributors to sea level rise: eustatic, isostatic, and steric changes. We'll also explore how scientists quantify and measure these changes. So how do we quantify sea level rise? Well, this is the sea level equation. It can help us track changes in sea levels over time. It might look a bit intimidating at first, but let's break it down and focus on what each part means. On the left, we have d eta dt. This represents the rate at which sea level is changing, whether it's rising or falling. Next, the eustatic term, which tracks changes in the mass of the ocean over time. This next term represents changes in water density, which is tied to steric changes. As the temperature and salinity of seawater change, so does its density. Finally, dHdt accounts for the vertical movements of the seafloor. This is connected to isostatic changes, where land can rise or sink due to geological processes like post-glacial rebound. Now that we've introduced the main contributors to sea level rise, let's take a closer look at each one to understand how these processes work in practice. It's not just about water rising uniformly across the globe. Different factors contribute in different ways. First up, eustatic changes. These refer to changes in the total volume of water in the oceans, largely driven by the melting of ice sheets and glaciers. When glaciers melt, that water ends up in the ocean. For example, Greenland alone loses about 0.5 millimeters of ice each year due to global warming. Now that might sound small, but when you spread it across all the world's oceans, it has a significant impact over time. Next, let's talk about steric changes. Now this involves changes in water density due to temperature and salinity. As water warms, it expands, taking up more space. This is a process known as thermal expansion. So as the ocean heats up, sea levels rise without any additional water being added. Changes in salinity also play a role. Less salty water is less dense and occupies more volume. Finally, let's talk about isostatic changes. These refer to changes in the land itself. During the last ice age, the immense weight of glaciers pushed down on the Earth's crust. As those glaciers melted, the land started to slowly rebound, a process that continues today in places like Scandinavia. Meanwhile, other areas are sinking, such as Jakarta and New Orleans, where subsidence is making these cities even more vulnerable to sea level rise. So while global sea levels might be rising, the movement of the land can drastically affect how much different regions actually experience that rise. So, with all these different factors contributing to sea level rise, how do we actually measure it? Well, it turns out that no single tool can capture the full picture. We need a combination of methods to track these changes accurately. For eustatic changes, we use satellite altimetry, which measures the surface height of the ocean using radar or lasers. This allows us to track changes in sea surface height over time. Systems like GRACE take it a step further by detecting shifts in the Earth's gravity to track how much water is being added. Tide gauges placed along coastlines provide long-term data on local sea levels and complement satellite measurements. For steric changes, Argo floats help us monitor temperature and salinity, providing data on how water density is shifting. So to summarize, sea level rise is driven by a combination of eustatic, isostatic, and steric effects. It's the combination of these factors that makes sea level rise a complex and important issue. So even though it might seem gradual, the long-term effects are significant, reshaping coastlines, impacting ecosystems, and threatening communities around the world. Thank you for watching.